Hi, and welcome back to Statistics 1. We're up to Lecture 5, and the topic of this lecture is correlation. This is a big topic in statistics. I'm sure you've heard lots about correlations or seen correlations reported in the news or on the internet or perhaps in research studies. And this first lecture, I'm going to start with a broad overview just to talk about the concept, and then we'll do some actual mathematical calculations, and then we'll talk about some of the assumptions underlying correlational analyses. So this lecture is split into 3 segments. As I said, in the first segment, what I'd like to do is just give you a broad overview of the concept of correlation and some examples. In the second segment, we'll walk through the mathematical calculation of the correlation coefficient R. That's Pearson's product moment correlation, which I'll have a lot to say about in segment 2. And then finally in segment 3, we'll talk about some of the assumptions underlying a typical correlational analysis. So let's launch into segment 1. The important concepts and topics to take away from this first segment is first, obviously, what is correlation? And then what are they used for? And we're also going to look at a lot of scatter plots. You saw some scatter plots in lecture 2 when I talked about the method of correlational studies, but now we'll really investigate scatter plots and look at all the details. Then there's a lot of words of caution. So I can talk about what are correlations used to do, and with the caution I'm going to say what are correlations not supposed to be used for. So we'll go through a lot of cautionary notes toward the end, and then I'll just list some other types of correlations beyond the Pearson product moment correlation, which is the one we're going to emphasize today. So first, what is a correlation procedure? It's just a statistical analysis used to measure or describe the relationship between 2 variables. Correlation coefficients can range between +1 and -1. A +1 indicates a perfect positive correlation. A -1 indicates a perfect negative correlation. 0, of course, indicates there's no relationship at all. That's independence. So a perfect positive correlation means as the scores on one variable go up, the scores on the other variable go up. Perfect negative correlation would be as the scores go up on one variable, the scores go down on the other. And I'll show you examples of that in scatter plots. It's best to just look at it in a scatter plot. So what are they used for? Well, we've already seen some uses of correlation in lecture 2. Very simply, if we have 2 variables, let's call them x and y, and they're correlated, if I know an individual's value on x, then I can predict their score on y, particularly if there's a very strong correlation. And there are lots of these examples that you're probably familiar with. One is IQ and academic achievement, right? So if you're high on IQ and I know that, then I'm going to predict you're probably going to do pretty well in school. Some newer research that's coming out, which is very interesting, is socioeconomic status in very young kids is also correlated with academic achievement. So if I know socioeconomic status, I might be able to predict academic achievement years later. Once we know that, hopefully we can do something to intervene with that relationship, right? So that's what correlation is mainly used for, to describe relationships, and then it's used for prediction, which leads us to the next topic, regression. So let's go back to this example of working memory capacity and intelligence. So I've mentioned that this is my area of expertise in my own research, and in the first lecture on experimental designs, we talked about this study and this whole sort of literature that's booming right now. It's actually an industry that's booming online, where people are trying to train their working memory to enhance their intelligence. Well, where did that idea come from? Well, it came from years of research, some of it done by my graduate advisor, Randy Ingalls, some of it done by myself and my colleagues, showing that scores on tests of working memory capacity are highly correlated with traditional standardized tests of intelligence, or IQ. So we know that working memory is correlated with IQ. So if I know a person's IQ, then I could predict how well they're going to do in my lab when they come and take a working memory task. So here's an example of a scatter plot illustrating that correlation. This is actually a really strong correlation. We exaggerated it just to make it clear that this is a very strong positive correlation. What we're looking at is a correlation between intelligence and working memory. So on the x-axis, I have IQ scores, and you'll notice that they're standardized, right? They're standardized on that z-scale. And I know that because the mean is 0. The same thing is true of the working memory task. So the working memory task in this example is the n-back task. That was the task that was used in that experimental example that I described back in lecture 1, where subjects had to do that n-back task every day for weeks. That was their working memory training. So the n-back task is a measure of working memory capacity. But more importantly, what this shows is each dot in the scatter plot, each dot is an individual. And the line that runs through the dots is called the regression line or the prediction line. And it just runs right through the middle of that scatter plot. And what this shows is if you're above average on IQ, then you tend to be above average on working memory capacity. That's a positive correlation. It's a pretty strong positive correlation. If you see up here, little r is 0.8. In the next segment, I'll show you how to calculate that little r, but just for now, know that that's a really high correlation coefficient. It's actually rare that we see them that high. Now, here's where all the cautionary notes and tales come in. The first one is one that you've all heard before, but to me, it's not really the most important one. I put it first because I know most people are familiar with it. So we know that correlation does not imply causation. Well, let's unpack that. What does that mean? It means that working memory capacity doesn't cause intelligence, and likewise, intelligence doesn't cause working memory capacity. There could be intervening variables. Most likely there are lots of intervening variables associated with the brain, particularly prefrontal cortex and parietal cortex. We know there's certain regions that are very important for working memory and for intelligence. So we can't say from this correlational study that one causes the other. They're just related. We know that they're correlated. There's an association there. So correlation does not imply causation. A great example my assistant David came up with is going to bed with your boots on is correlated with having a headache in the morning. That's an association. It doesn't mean having your boots on caused the headache. What's more likely is that you were drunk and fell asleep with your boots on and were hungover in the morning, and that's why you had the headache. There are lots of fun examples of this if you Google correlation fun examples. So I think we all know that correlation does not imply causation. More importantly, and this is what I'm going to focus on in lecture 6 primarily, is the magnitude of a correlation depends on a lot of factors, including sampling, which we've already talked about, that idea of getting a random and representative sample. It also depends critically on measurement of your variables, so measurement of x and y. Specifically, do you have reliable measures and do you have valid measures? So for example, in the intelligence literature, we need to know that we have reliable assessments of intelligence. We need to know that they're valid assessments of intelligence in order for us to make any sense of the correlational analyses. So we're going to spend a lot of time talking about that in lecture 6. For now, let's just look at one of these assumptions, the idea that we have random and representative sampling. So I showed you that there's a strong correlation between working memory capacity and intelligence in healthy young adults. And I've seen that in my own research. It's been replicated many, many times over the last couple of decades. But that's if we look at all young, healthy adults. If we get a heterogeneous sample of, say, all high school graduates. What if we relied on a more convenient sample at, say, a prestigious selective school of higher education like Princeton. And we might want to ask, what is the correlation between IQ and working memory among college graduates? You'll see that's not a random representative sample of all young adults. It's a different kind of sample. So let's look at that scatter plot. This is a bit exaggerated again. We made up the data, but now you'll see the correlation is not very strong. It's only 0.2. And why is that? Well, if you look at the IQ distribution, again, we exaggerated this, but everybody's above average on IQ because they're college graduates. They were selected into college most likely on the basis of some sort of standardized tests like an IQ test. So this is not that far-fetched. And actually in my own research, I did look at the relationship between working memory and intelligence in a selective institution, not Princeton, and the correlation was 0.22, where I'm used to finding a correlation of about 0.66. This is known as attenuation of correlation due to restriction of range in one of your variables. So the fact that we only have these really smart people restricts our range. In other words, it restricts our variance, which doesn't allow for us to find covariance. And finally, this is the last cautionary note, and it's perhaps the most important for general consumers of statistics and particularly correlations, is a lot of people get upset when they hear that, say, your score on some standardized tests predicts how well you're going to do in college. But it's only a sample statistic. A correlation coefficient is a sample statistic, just like a mean is a sample statistic. And it may not be representative of everyone in the sample, unless the correlation's 1.0, right? So I'm a perfect example of this. When I took the standardized tests here in the US, they're called the SAT. I scored really well on the math and really poor on the verbal. That's why I'm a statistics teacher. And in school, I tended to have very high grades in math and science, but not so high in things like history and language, despite the fact that those things are correlated, right? If you go back to lecture 2 on correlational studies, we saw that this was the example I used for a moderate correlation between, say, math and language. So if you look at the dots, you see that on average, as you go up on one, you go up on the other. But let's say this is math, and let's say this is history. I was like this guy out here. Off the charts on math, but really below average on history, frankly, because at that age, I didn't have the patience to sit down and read long texts. So I didn't do very well in things like history or English. I wasn't quite that low, maybe about there. But the point is, as you go up on one, on average, as people go up on one score, they go up on the other score. That's a positive correlation. But it may not be representative for every individual in the sample. Okay? That's one of the most important things to take away from thinking about correlations. This final note is there are several types of correlation coefficients depending on the types of variables that you're looking at. So go back to lecture 3 where we talked about types of variables. I'm going to emphasize this one right here, the Pearson product moment correlation coefficient, or little r. That's what we're going to focus on in the next segment. And that's the most common one because it provides us with the most amount of information. We have a continuous variable x and a continuous variable y, and we can look at the correlation between the two. If one of our variables is continuous and one is dichotomous, if it's just 0 or 1, then there's a different coefficient. It's called the point biserial correlation coefficient. Also, if we have two dichotomous variables, if both x and y are dichotomous, then we'll calculate the phi coefficient. And if we have both x and y as ranked or ordinal variables, then we can calculate what's called the Spearman rank order correlation. I'm just listing these here so that you're aware of them. For now, since this is just an intro stats course, we're going to focus on just the Pearson product moment correlation, little r. It's by far the most common one that you'll encounter. But just remember, and for your own knowledge, know that there are other types, and it depends on what kinds of variables you're looking at. So to sum up this segment, we talked about just what is a correlation, what are they used for. We're going to look at scatter plots a lot when we're talking about correlations. There's a lot of cautionary notes that you have to keep in mind. And then remember, there are different types of correlations depending on the types of variables that you're analyzing. And that wraps up this segment.